Okay, chapter 6, section 3, the central limit theorem, or the CLT. Here we're going to just give a brief introduction to the central limit theorem and what it says, and we're going to talk about the sampling distribution of sample means, or you could just say is the sampling. I don't know. I guess we have to say the full whole thing, but maybe we'll figure out a way to abbreviate that a little bit. So what this is the essentially we take the whole entire set of data for the entire population, and we imagine taking samples of size n, all possible samples of size n. So this is kind of what I'm trying to simulate with the group projects that I'm having you do, is why you're in so many different sample groups. Is because I'm taking or I'm trying to take as many different possible samples of size 6 for our particular case. Might have to amend that because different groups may not have 6 in them. Canvas. Anyhow, so what we were doing here is we're taking, this is the hypothetical distribution of all possible average values of all of the samples selected from the whole entire population with replacement. So basically it means kind of like this. We take 6 of you. We say, okay, calculate your mean. All right, now put you back in, get a different 6. I mean, 5 of you could be the same as long as we pull one extra person. That's a different group of 6. So the 5 of you went back into the pool and you were reselected. Okay, so that is what the with replacement that you might see in the book means. So it's our distribution. So all of the values in this new space, this distribution, are actually not data values themselves. They are averages from samples. So all of the things in our distribution are chi-bar, right? Sampling error, what is this? Well, this is one thing that we want to really pay close attention to. Sampling error is the difference between the measured value or the computed value from the sample. We refer to that as the statistic, and the measured value or computed value from our population, or in other words, the parameter. Okay, so this distribution is something that we can examine with a whole lot of fancy mathematics. And basic properties of this are, well, no matter what the central limit theorem basically says is this: we cannot assume that our data is normally distributed. We can't assume that. We have encountered different data sets that are skewed one way or another, or are uniform, just flat line distributions. So we could even have, we could have all manner of different distributions that are not necessarily normal distributions. And what the central limit theorem allows us to do is, instead of looking at just one particular value, we'll take a sample. And that sample is something out of this distribution of sampling means. And so the nice thing about it is that as long as we increase our sample size enough, the sampling error becomes small. And essentially, this distribution itself is normally distributed. Okay, so the properties that we are going to go over here is, first of all, we have this new set of values, let's call it, our averages from all of the samples of the same size. Okay, so the average of that whole data set, that whole set of values, I've denoted as mu subscript chi bar. Okay. When we selected subgroups of 6 of you throughout the class, I only had to do 6 different ones. But in theory, you could do many, 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 many more groupings of 6 of you and compute your average age. So this, in fact, is a population mean because there is, whole quantity, whole numerous quantity of all of the various different subgroups of 6 that we could take. And I'm just using 6 as an example because that's what I gave you in your group project. Okay, that average from our new space of sample means is, as we might expect, the same as the average from the whole population. So this is one thing that we'll be looking at, is how close is our average for our particular sample close to the population average. What would that difference be? That would be our sampling error. Okay. And then second of all, this is the part that becomes a little bit strange, I guess. This part is the same because we can kind of just say, okay, mu is mu, and not have to bother with the subscript. But then this next little part is going to be weird. Okay, so here the subscript makes a difference. The sigma subscript chi bar, that denotes the standard deviation of this distribution, not the original distribution. So what this is saying, first of all, is the standard deviation for our new sampling distribution of sampling means, this new space, is lower than the distribution, the standard deviation for the distribution that we're originally considering. And then second of all, we actually have an estimation for it. It's not just less because we're dividing it by something. We know exactly that it's proportional to the original standard deviation for the original distribution divided by the square root of whatever that sample size is. So what this means for us is that we have essentially a different way that we have to compute our z-score, but we still get to compute a z-score. That's the good news. All right. So the bad news is you gotta remember a slightly more complicated formula. The good news, though, is that we get to use this same exact technique, and it's actually, fairly not too bad considering all of the different complicated things that we could possibly have to do. So remember, a z-value, how do we do that? That is the value from our distribution minus the mean of the distribution, okay, all divided by the standard deviation of that distribution. So I made a point there to emphasize from that distribution, from the distribution, etc. Because the value from this distribution, remember this is the sampling distribution of sample means. The values in this distribution are going to be sample means. So we make a big deal of saying that's chi bar, right? Right over here, the mean of the distribution, going back up here, the mean of the distribution that I'm referring to is the distribution of sampling means, so that's why I have the subscript of chi bar on this mu. That is the mean of the distribution that we're looking at, the sampling distribution of sampling means, that mouthful. But the nice thing here, I said, is we don't have to put the subscript because this mean and this mean are identical to one another. The bad news, though, is this. We can't just put sigma the sigma for our distribution, the standard deviation for this new distribution, the sampling distribution of sampling means, is sigma subscript chi bar. And that value is related to the original sigma. It is exactly equal to sigma divided by the square root of the sample size, which we'll denote by n. Okay, so that new formula is the new way that we'll be computing the z-score. Now we have to remember that the sample size is going to factor in. That's going to make a difference. All right, so let's pause here and we'll move on to the next example and do that quickly. Okay, so coming back, example 6-13, looking on page 347. And it's pertaining to hours that children watch television, so it gives us children ages 2 to 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed, and the standard deviation is 3 hours. So notice here we don't have to actually assume that the variable is normally distributed, but it's a nice bonus. Okay, so here the giveaway is that we are selecting 20 children in this age range from 2 to 5 randomly. And we're going to ask about what is the probability that the average number of hours that this sample of 20 children watches will be greater than 26.3 hours. All right, so here, the distribution of sampling means of size n equals 20 is what we're going to be looking at here. So I've written this as what's the probability that chi bar will be greater than 26.3. So not just x itself, but the average of this whole sample of 20 children. So here our chi bar is 26.3. What we're going to be looking at is, well, we have our distribution, which is approximately normal. It's not supposed to touch, so never mind that. It's not supposed to be perfect either. And here we've got mu equals 25 in the middle, and then over here somewhere is 26.3. And we want to know what's the probability that the average for this group, television hours per week, is greater than or equal to 26.3. Well, I guess not equal to, greater than 26.3. Right, so we're looking for a right area here, right? But this is not the distribution itself. This is our distribution of sampling means, chi bar, right? So that just means that when we go to compute our z-score, we're not just going to put in an x value, we're going to put in the average. So the average being 26.3 in this case. That's the critical value that we're looking at. We're going to do this minus 25. That's the average of the distribution of sampling means. Is the same as the average period. Okay, but then here we're going to put in not just sigma, because remember sigma for our distribution, chi bar sigma, is going to be sigma divided by the square root of n. And so in this particular case, we're going to be putting in 3 in place of sigma and then dividing by the square root of 20. So here in the denominator, I'll put 3 divided by the square root of 20. All right, so we're going to go ahead and calculate this z value. Already done this in my calculator. I wanted to kind of walk through it and show you, but I don't know if the contrast is showing up very well there. Notice I've included a lot of parentheses because of this, where did it go? This double division aspect. First of all, I included parentheses around the first part to just make sure that we were doing that subtraction